Welcome back to the Live Coding Alliance live stream. My name is Cale, and we're hacking on the low rank recurrent convolutional number generator that I came up with. It is a CPU based random number generator. Does it say day 2? Oops, day 3. What am I going to do? Right? So it's a CPU based neural network, and I do e to the x and find logarithm, square root, and every time I do a division instruction, I XOR a running XOR. So, and then anytime I use it, I have to set it back to 0, which I don't have in the code right now. So I remember to do that. But the the algorithm trains the neural network little by little each time you generate a random number. So, I'm trying to keep it down to like under 100 divisions max. But most of the time, you don't even have divisions. The divisions, they happen so in order to be able to detect whether or not I have a normal distribution, I got to go run through a loop and do some statistics calculation. So anytime I have a division in there, do the running XOR with the result, and so that guarantees that I have enough pseudo-random bits in order to take an input random number that's between -1 and 1 and XOR them together. Or sorry. Yeah, XOR that with a running XOR. And then we end up with a random number. And so, I could just do it with only the pseudo-random numbers, but the more randomness from different sources, the better for the random number generator. It's like, it's just one more XOR, so it's not a huge amount more random, but if it's not a normal distribution, aka a bell curve, then I run my neural net algorithm. And so let me show you the architecture that I got. This is cool. I think that this is awesome. First of all right. Here is. Don't you wish you had that? It's just a cheap 4K HDMI camera, Makos HDC 20, I think. HDC 10. All right. I think I paid $50 for it on eBay used. And then I got an HDMI capture card, and it's 4K. I got a aftermarket 4.35 millimeter 10 megapixel M12 lens on eBay. Is she really doing that again? Stop that. No. Sorry, I got a rabbit eating my wall over there. It's constant bugaboo. I think she just wants my attention. So, I gotta stay on point. We got a low rank adaptation, which means, or a LoRA, LoRA, not to be confused with the wireless protocol, which is a little bit, I don't really like. It's confusing. It's hard to get the right information. So what we have is we got a LoRA matrix. Probably shouldn't have scratched this out, but A1, A2. So I don't have the subscripts in here too. So this is like you do a matrix division. I'm sorry, I was having a brain fart, man. you multiply the matrix and then, sorry, I don't have subscripts in here correctly. What is it? I9. No. Down in the corner. And so along the diagonals, what we're going to get is a product of, A times A. Sorry, this is supposed to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then A, B, C. Shoot. Right. Maybe I could redo that. Let's just do down here in the corner because I just botched that so bad. I'm going to do A, B, C. And then we're going to do transpose D, E, F. This results in a 3x3 matrix where it's A, D, and then we got B, E, and C, F up in the diagonal. All right. So, what does this mean? Right. This is actually interesting. So this means we have a neural network. So this is how the dimension, this really reveals how the dimensionality reduction of LoRA actually works. So we can see in the diagonals, these two things are actually like a product of each other. So actually, really, what it is we have it's like we have 3 neurons right here in the diagonal, and then these neurons are made up of another mathematical formula. So it's dimensionality reduction, basically. And so going back to this is a 9x9. So we do our LoRA, and then here in the diagonal, we're going to get the neural network that we're going to feed in to this side. And we're going to move the random numbers up from 9 neurons to 8, 7, all the way up to here. And then this is where our random numbers are going to be. Maybe I should just put a star. All right, so what did I say was I had a theory. If we wanted to output like a random probability between 0 and 1, that we would want these two perceptrons to scale from a -1 to 1 input to a 0 to 1 input output using these two perceptrons, and I thought maybe we could figure out some sort of fitness function with these two. But then I have to like, what would this be? This would, let's say 1, 2, 3, 4, 5, 6. What do I do? I don't know. It kind of makes my brain hurt. I want to do some programming because that's a little bit too complicated, but that's what I'm doing. I don't know if anybody's ever done that. I just, I wanted to generate random numbers. So because I want to take one 64-bit random number, pseudo-random number, and I want to generate 2 actual uniform distribution random numbers using, less than 500 64-bit floating point values. This, if we got a neural network with 500 64-bit values, it's not a whole lot for a CPU. So we're not going to be getting bogged down with that, especially if we're only doing training just a little bit at a time. I'm going to have different test cases. I'm going to have to benchmark it to a fully connected. See, because the problem, the problem is, like, let's fully connect all of these layers. I'm on a CPU, it's like 64-bit CPU. So, I mean, even with just these, let's just say I had a square. Well, I guess it would be like this. Or, that's 1, 2, 3, 4. This is like, I think that this is enough perceptrons. If they were fully connected right here, I think that that's enough to generate a random number. I think that these are going to do a better job with the inclusion of these perceptrons. But, you got to look at how many, like if we were just going to generate one random number from this, and we had a fully connected layer, right? It's going to do a better job of finding patterns in it. But the question is, like, how good of a job does it really need to be? Right. Because we want it to generate random numbers as fast as possible. And we would prefer to not do any unnecessary calculations. Like if we could just go one loop through the whole standard deviation calculation and all the other calculations that we need related to that, just to see whether or not it's a uniform value, and then not have to iterate through like 4,000 times, and then only have to do that like maybe one in 10 times. I think that's going to be quite a bit better, especially, if we're only going through, let's say we have to go through Newton's algorithm or the Taylor series for e to the x. Or is that the Maclaurin? She's chewing on the wall, and she's doing it again, too. No. Don't make me come over there. And listen. Stop it. Oh, she won't stop eating the wall. All right, what do we got here? Add that to the dictionary. What is it? Can't just do this, huh? Log and divided by W. This one's expensive. but not too bad. 2 times log. What the hell? I got this code from Wikipedia. Their code was garbage, dude. Yeah, I'd update their code, but they blocked me. Oh, sorry, I'm looking at the wrong. All right, so okay. So how exactly do I go about doing this again? So let's look at the algorithm that I have. So I start off with the dirty exponent. Dirty and then the clean. So all the exponents have to be 51. Because then we get the 53 bits. -1 to 1. So it's like the maximization of the dynamic range. Notice I did the hand waving. You're like, what are you talking about? 51, what does that mean? It's IEEE 754. The way they do the floating point. So all the exponents are 53 and or 51 in great, sorry, 52 and greater are just integer values in the antissa. They shift, and there's no hidden bit. I didn't know that till yesterday. I thought I knew more about that. I guess I haven't done a whole lot of work with the specification, so there's probably a lot of other things that I don't know. All right. So what do we do? We eject. So how do I? So am I generating pairs of samples? LN. I'm confused. What log? I think he's using the. So sample. Do I need 2 samples in order for this algorithm to work? So what is this thing doing? Is it taking the average and then So u.u plus v.v. What is this going to tell us? We're working with probabilities here, so they're all less than 1. Greater than -1. All right. What am I doing? So are they like... Oh, so they just taking like a pseudo-random number generator and then... So what, I need 2 random numbers? So what does this mean with my 12 sample? I need 12 samples to do the normal distribution. But I'm not adding them up. I think I like mixed up the algorithms, and we got the what do I take the last one? I could take the last sample in the that came in, and then like this is fine in a loop, but this isn't like how my algorithm works. This one's significantly faster. I don't know. I like the idea of the client generating a random number, because for the purposes of generating a random number for like a web server, having as much randomness as possible is going to be better. So like this thing's having to go through a loop a number of times. So what if I just did one of these is the running XOR? One of them is the client generated random number. Okay. So then I, what, u dot f, u times, look, you return the generate Gaussian. I'm confused. What am I returning in this algorithm? This must be the Java one, right? Random. Times 2 minus 1. So what does that do? That makes it positive. So I did random. What is this? Oh, this is C++. Well, I don't use the C++ standard library. I got my own library. What is the description of this thing again? Generating a pair of independent standard normal variables. So, but shouldn't all of the last 12 samples produce this? Like, I mean, this is great for like, you have two random samples, right? But I have one random sample coming in from what do I do? Do I like, so what if I just took the XOR? So let's say the client generated a random number. I generated a random number. I determined that these two values were a uniform distribution, right? Then I XOR them, right? And then I check to see if that fits a normal distribution. But what do I have to do with this? I mean, I could check the last value. That's the other. I mean, it makes sense to check the last value with the current one to see whether or not those two match. Right? Okay, so that's what I'm going to do. Let's go into this. I got the idea. So first we're going to take the, here's the old sample. Is that the eject? Do we take the, maybe we do it from the eject. We're already ejecting one, right? It makes more sense if you ask me to do the polar rejection test with, so what do? Do I take the, all right, so dirty, so this is my dirty probability. I like calling it a dirty probability and a clean probability. There's just something about the wording of it that just, it gives me joy. It makes me want to smile. It makes me think dirty things. Okay, so I have two options. I can pre-increment or post-increment. I'm going to post-increment. What about sample count? All right. Okay. History index. This isn't the same thing, but what do I got to do? What index? Mod sample count. No, no, thank you. cats are fighting. I like a stray cat showed up. I got porch cats that were also strays, and then there's other really pretty orange, really fluffy tabby cat stray. He showed up and just like took over the porch, and like we try to like pet him, and like bat at us and hiss, and you know it's been a week and he's getting better. He's so cute. I mean, I don't think he's gonna like attack us. You know, you just, if I can't get my hand out of the way when he's batting, then you know I deserve to get scratched. Yeah. Sample. I know it's not as strong, but this is more convenient. Sample. It's way better, huh? Less optimal. What is it? Clean probability? Alright. So I evict using the last evicted sample. And then what do I do? This thing is missing this whole this square root. So what is it? This is I don't like this. Let's go with so we need U and V, and then what are they happening? I'm just doing it in a while loop. So what do I want to do? I don't like how they did not use consistent naming in Wikipedia. I thought their code was absolute garbage. I mean, come on. No JavaScript version. I want to upload the JavaScript version. I'm not going to do this in this loop though, because I don't want to pay the price for I mean U and V. Is this text? Is that polar method? Okay, I'm happy with that. Like, this one is, oh my god, man. Really not happy with their code at all. Z1, like, like their code wasn't consistent at all. Okay, so we do S, and so S is I don't. This code is so bad. What are you doing? S is greater than equal 1 or S is. Sorry, I'm not thinking. So if it's greater than 1, or if it's equal to 0. So what does it mean if it's equal to 0? S equal to, it means what? Both of the terms be 0? Well, I mean, that's better than checking to see if they're both 0, right? And then S is equal to what? Log F over F. And then I'm returning mean plus the standard deviation times U times F. These algorithms are just not consistent at all. Like, honestly, it's frustrating. Okay, so what's up with this part? So the mean plus the standard deviation plus U times S. And then that's what? That's like a U times S? Hold on, this is double mean and standard deviation. Okay, so these are parameters that we could set. Okay. Mean and standard deviation. Times U times S. So what is that going to make? So what is that what we're doing with? I'm sorry. I guess I didn't actually pay too much attention to all this gibberish up here because I'm pretty good at math. So I'm just kind of spiraling around like, what the hell is this shit? So what the hell are we doing here? And what do we do when we multiply the ln of f? Here, let's look at the what I need to know. So the -2, isn't that like something to do with the derivative right there? Is it like the natural logarithm squared and we're taking a derivative or something? And then it's over S. Every time I see S, I think of the Laplace transform. It's hard for me. Like, are we in S domain? Cosine and sine of the angle at that vector. Okay. And so here, let's see if we can find a video that explains this math, because I think that this is a very interesting video.
Hello and welcome to this video. In this video, we will learn how the Salia generator works.
I'm sorry, I have to do double speed, dude.
Or even any kind of variables. In this video, I will make some references to the Barcelona video, so I suggest you watch that first. This method is in some ways better than the Barcelona method because this method avoids the so-called trigonometric functions. I will start by going through the theory, and then I will implement exactly how to see this algorithm works. Now, if you enjoyed the video, please give it a like, subscribe, and well, let's just please enjoy this video. Okay, now I'm ready to go through the theory. So our goal is to simulate x from a standard point. The algorithm which we will use to do this is this Salia algorithm. Here we sample u1, 2 from a standard. Oh, sorry, I standard from uniform minus 1.
Okay, so what is the benefit of me ejecting? I'll go into my probability, I eject my sample. Okay. So then I would do what do I do? F this dot. Why did I not make that con for the eject? And then no. Don't I need to clean out? It's expensive to run this. I only want to run it once. Right now, I'm keeping track of the dirty probabilities. The dirty probabilities are the probabilities that are either pseudo-random or poison. Okay? So I'm allowing clients to generate random numbers and then submit them to me, where then I then do some magic and then only have to do like 100 division instructions, and then I get you a perfectly uniform distribution number, or it might even be even less than that. But each time I generate a number, I have to go through this cycle of ejecting the last one, checking to see if the new one is a good probability. So let's say somebody's trying to hack my UUID generator. So the current dirty probability is the most recently submitted one, but in somewhere else in there is another poison sample, or maybe they're all poison, right? What would poisoning look like? Poisoning would look like probably repeating the same numbers in a sequence. But the thing is that I'm randomizing. So I don't think that it would really matter if they poisoned it. Let's say they submitted like the same probabilities that yes, they form a normal distribution, but you're cycling them over and over again in order to get the same output. Would that actually affect my algorithm? I don't think that would. I mean, then there's an argument to be made. Why am I taking any sort of samples from the user? I believe that this is a method to detect bad actors. So as easy as it is to hack a lot of systems, I'm not saying that this one's easy to hack, because there's no way you could figure out what my neural network values are based off of the XOR of like 20 different division instructions. It would be impossible for anybody to figure that out. It could be so many different things. It could be an infinite different combination of things that nobody could figure out. Not even a neural network, because it always changes. The neural network might be able to emulate the pattern that I used, but that pattern in the future would change, and it would be very expensive, and it still wouldn't output the same numbers. It would output similar numbers, but it would not output the same numbers. So I believe that it's like icing on the cake, if you ask me, the taking in a dirty probability. I think it's okay. If our system is completely tolerant to poisoned dirty probability, I think you've got a pretty good system there. sounds like the one that I want to use. It's like, oh well, it's just icing on the cake. It makes it a little bit better. You know, we just take a little, because we got to assume like what percentage of these actors are going to be bad actors. Well, if I have like no users and the first user that I get on here is a malicious actor, I mean, well, yeah, right. But how are they going to be able to hack the next UUID? Let's say that somebody is connecting to my server and they are utilizing the system correctly. Okay, and then somebody wants to jump in and they want to hack their UUID so that they could compromise the system, and then maybe they could masquerade as another user, see data they weren't supposed to see. Okay? I personally don't think that you could do that with this, because the moment I take your dirty probability and then I XOR it with my clean sample, okay, hold on one. This is the clean sample. The dirty sample. Oh, do I not do anything with the dirty sample? Okay, so I think I need to do it after here. I'm just ditching the dirty sample right now. It's for like statistics. Really what I would need though is I would need to keep the last 12 samples from each user. That's a possibility. I like the idea of storing each user that's connected to a server in RAM, so that whenever they connect, I can get information about that IP address. Especially, if it's like a test. Like, is this a malicious actor? Because let's say that it's a robot that doesn't really know. Let's say it's like a really powerful AI. This AI is trying to hack my UUID generator here. Sub-second ID. You can find it on GitHub. So that, I think, is more likely than having a hostile actor who's trying to like hack your UUID thing. Okay, so what do I do? Is this the second thing? Sorry. So eject and what do I need? Clean. Where's my clean probability? I'm confused. What is the? Am I? I guess let's go back to the lesson.
Distributed until you 1 square plus root 2 square is less than or equals 1, and we call this r squared. Then we return a set equal to 1 times the square root of 2 times the logarithm of r squared divided by r squared. Then I claim this, and this is what I want to prove, that set has the same distribution as x. So that is, set should be standard normal. And this is far from clear, and this is going to be a long video because there's a lot of theory going into proving this. But finally, in the end, I will go to a Python example where I show that it works practice. So let's go down here to the left 125. So let's consider a pair U1, U2, where we sample them as a block. If we draw a coordinate system, that means we have minus 1 here, we have 1, this is going to be even, here, 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 1, minus 1. Then our U pairs will lie within this box. So somewhere in here, our U1, U2 will lie. We then keep trying until r squared, which is equal to 1 squared plus U2 squared, is less than or equal to 1. This is the same as r being less than or equal to 1. And r is exactly how we can find the radius. This is the radius of distance from orbital to this pair. So we throw away all points which fall outside of the unit disk. This disk has radius 1. And we throw away the pairs where this radius is greater than 1. Now, if we consider some point, if we say this is our point, U1, point U2, just put it up here. Then instead of writing the coordinate as one coordinate and the other, we can use polar coordinates. So we can write it as distance and the angle. So this is the radius, this is the angle. Then U1, point U2, can be written as the cosine of theta, sine of theta, and then both multiplied by r. Okay, we have established that our U1 and U2s are identically distributed within the unit square. That means that the distribution U1, U2, taken sub U1, U2, will be equal to 1 divided by the area of the unit square, but that is just pi. Now I want to somehow find the density of theta and r. We know these can be written. We know there's a function f1, which takes U1 over into the cosine theta multiplied by r. Just probably write the r on the other side. And f2 taken U2 over into r sine theta. So the way we find this distribution is that we take the distribution of U1 and U2, and then we multiply it by the determinant of the Jacobian matrix.
Oh god, the Jacobian, no. What is the Jacobian again?
Is the matrix ready? This is going to be a bit too small. D f1 theta, D f1 r. So we take the derivative with regards to one variable then the other, and then we do the same for the other function. So this function is r times the cosine of theta. So this will be equal to r times minus sine theta. Now here we will have just cosine of theta. Up here we have r times the derivative of sine theta, which is cosine theta. And up here we have sine theta. So we get that this the determinant will be equal to minus sine theta squared. So we take this entrance, move down to this one, that is r sine theta squared, and then we subtract this entrance with this one, we can take the r outside, and then we have cosine theta squared. Just make the square again. Okay, so when we take numerical value, we just get this minus disappears, this becomes a plus. Then it's a well-known result, and this is equal to 1. I'll include So we get that this is equal to r. So if we go up here, we can write this as 1 over pi multiplied by r. Now, we can write this in a different way. We can write this as 1 over 2 pi multiplied by 2r. Nothing has changed. Then we can say that this is the density of beta. This is the density of r. Then we have that beta and r are independent since they're joint. The joint density is split up into a product of their marginal densities. Okay, this is very important that beta and r are independent. Now I can say I claim that r has the same distribution as the square root of the uniform distribution. So consider this, consider square root u being less than or equal to some r. That is equal to probability u being less than or equal to some r squared.
All right, so I'm just thinking about this. So, like, when does u squared plus b squared become greater than or equal to 1? That would be u squared is equal to 0.5, right? Right? So then just 0.5 divided by 0.5. So let's take 0.75 plus seven. When I couldn't have like 0.9. So when is this going to be a problem? So let's say, the input sample is 50% chance that it's going to be, oh yeah, okay, so first off, you got to remember the input is -1 to 1. In my head, I was like, what the hell is going on? Because, like, that would mean that, if it was 0 to 1, and then we did the square, then, let's say, like, we had 0.75 and 0.9. Okay? So just 0.75 and 0.9, if you threw those in a bucket, those would not form a uniform distribution because they're skewed off towards the far side. But it's not like a unheard of number combination. I mean, it's pretty common to have a distribution that's like that. Let's go back to the thing. Because you got to keep in mind that one of these numbers is going to be negative. So when you square, I don't think he's gotten to that part. But.
This would be equal to r squared. This is the CF of u, or this is the CF of square root u, taking an r. So to get the density, square root u, r, you have to take the derivative with regards to r, which will then be 2 times r. But this is exactly, instead of a large r here, this will exactly be equal to the density of large r taken an r. Because we found up here that this density is 2 times r. I should have used a small r here. So this is correct. Okay, now I claim that u1 squared of ordinary affair plus u2 squared is also uniform distributed, where this is a standard, and then this is independent of beta. So consider u1 squared plus u2 squared. This is equal to r squared. This is equal to r squared multiplied by the cosine cosine squared theta plus sine squared theta plus this is equal to 1. So this is equal to the radius squared, but the radius squared has the same distribution as some uniform, or r has the same distribution as the square root of some uniform. So this square has the same distribution as the uniform. So this time, also we know that r is independent of theta, which means that the function taken of r will still be independent of theta. So this claim is also correct. Now I claim my own thing. I claim that E1, a plane phase standard expansion, has the same distribution as minus the logarithm u, which then has the same distribution as minus log r squared. Now, we consider the probability of minus the logarithm u is less than or equal to x, then this is equal to the probability if we multiply by 1 over minus 1 on both sides, then we get that inequality turns around, then we take the exponential on both sides, so we get that u must be larger than or equal to the exponential function minus x. This is the tail function of the uniform, so this is equal to 1 minus this guy. But this is exactly the CDF of a standard expansion taken at x. So this is also all right. Now, finally, we have that a pair x1, x2, where x1 and x2 are IID all to the 1. This I argued in the particular algorithm and written as cosine theta, sine of theta, multiplied by square root of 2 times a exponential 1. And now you can probably see that we can tie all these things together, because we can also write this as, we know that cosine theta, sine theta, we know that this can be written as u1, u2 divided by r. We originally wrote that this pair was equal to r times this pair, so we can just drag r over to this side. We just proved that this factor has the same distribution as square root of 2 multiplied by minus the logarithm of r squared. That's what we just did up here, because r squared was given under this degree. And now you can probably see where our algorithm comes from, because we can just put this r inside this over here. So this is 1, 2, multiplied by some factor over here, 2 times minus the logarithm of r squared divided by r squared. Since we only want to simulate one of these, we only take the first order. So h1 has the same distribution as the first order up here, u1 times square root 2 times the logarithm r squared divided by r squared. And this was what we wanted to prove. Now I'm going to open up my pie chart, then I will show you that this actually works backwards. Because it can be a bit hard to see why this works just using this theory. Yeah, so I'll see you when I open my pie chart. Okay, well, this is my pie chart. Now I will build up my code using LBM indexes to basically grabbing everything up. So first of all, I import some packages.
Boot.dev's biggest sale of the year is live. Get 40% off
Boot.dev
your
is
next
live.
year of
40% off, you guys.
Then on my repo, then on my package is tools and square roots, import methods of storing data. Then the random object lets me simulate my field and variables, and then the rest are used for good blocks. So my simulations, well, I will need to simulate my one, my two, and then I have to calculate my r squared and see whether or not this is less than or equal to 1. So I go, well, this is the function I use to make my output. Where I take u1, I take my r squared, then I return u1 multiplied by the square root of minus 2 times the logarithm of r squared divided by r squared. This is exactly what we just showed in f3. And then finally I go to plus. I have to be a bit careful now, because I actually have to build the function. It simulates my x's, and takes my n, which is the amount of equations I want. So for I range up to n, I then I can set r is q equal to 2, for example, something which is larger than 1. While r is q is larger than 1, I then simulate u1, I simulate u2, and I define r squared. This will keep happening until r squared is larger, or is less than 1 when it stops. Then define this function. I will need an output, which I will need here. Output equals 1 minus zeros. These. This function will just go all the way outside. So at this point, I have sampled u1 and u2 until they are within the unit circle. So now I build my x, which is equal to f of u1 is q, where f is this function up here. And then I append my x, my output. Then finally I return my output. Okay. Then up here I simulate 7,000 realizations. This should be standard only. just trying to make different bits first. After I wanted, make 100 bits stuff for this particular trigger. You can see that there are overall the bits quite low. It should go fast enough. So you can see that this curve fits very, very low in our distributions or with our oscillations. And we could then transform this hex such that we have another power distribution. So this is standard power distribution. But I will not do this. I did that after all video, so you can see it there. Very interesting.
Okay.
And sweat.
All right, where's the code? I don't want to waste any more time. What are you doing with this? Is he doing something different? Because I'm not done. Multiplying by 2. How can I do that? Huh? Running excellent. Oh, I just got lost, huh? I'm just confused, like, what is he... Is this different? Because he's doing... What is he doing? Yeah. Is this like a private function? I haven't programmed in Python in a while. I need to jump back over to Python. So what does this do? So r squared, what does that do when we're... I remember that shit from linear algebra 2. I don't remember... I remember u dot u dot plus v dot v. Because yeah, can't you expand this into multiple dimensions too? Yeah, I can't. Can I do that? Multiple dimensions with this? maybe these people didn't think about that. That would be actually kind of clever if I could do that, like a matrix of these. So what's the idea? What do I have to check to see if it contains? What's the probability chance that it contains this number? I need to like check if sample exists. Like, no, I want to pass my samples in like this. Where do I do that at? Guess I need to have more space. Huh? Where's like 86 right there? That's more than I want. N per trigger. This is 82, son of a bee. How about cycles through calculation each per and this is back to 85. Still at 82, son of a bee. I'm just not going to deal with that right now. It's not high value. What did I just do? I'm lost. So we got a clean probability. I think if I just have so what am I doing here? So this was the other technique, and I'm not using this technique anymore. So I don't know if I want this. And what's the point of having the last 12 samples? Well, I can get statistics on it. Find dirty probability. What do I do? Oh, this is the problem. Um, Okay, so if I ran this loop on all my samples, it's definitely going to be way faster than the other one. The square root calculations, not super expensive. The logarithm one, that one's more expensive. Anything with a division, especially in a loop, is going to be expensive. I'm just kind of confused. Like, what is the... Seems like it's like foolish to not XOR that. Like I got two numbers together, and then, you know, you can XOR them, and then... Thinking. Shoot, man, I'm having problems here. So log. How do I calculate log? I have an algorithm, right? Oh, I let the AI. This is vibe coded, dude. Hold on, this is tab autocomplete generated, and it might be completely whack bullshit. What is this? Divine. Log. So NP log is that's like is that in a log again? Base what? A natural logarithm? Why? Why? Well, I mean, maybe I can see the point of saying if there's only one log, then you would call it. I mean, we would have to have the not natural logarithm because you could scale all of the other ones into the natural logarithm. Oh. Okay. So these people are rude. I haven't programmed in Python in a while. I should know this, dude. I do not want to call this. I'm sorry. It wouldn't make sense if it was log base 10. It would have to be a natural log. All right. What is that? Newton's of it? Okay, this is pretty slow, dude. This is Gemini 3 Pro, by the way. better, whatever this is, like, easier to see over here, right? Why not do? Hmm? I guess we don't do. Down here. I hate that calculator. Where'd my calculator go? Oh, I hate it when my calculator's not where it's supposed to be. It's always really shitty. You gotta get an extra one. Oh, I want more progress though. Like, I don't feel like I made a whole lot of progress here, other than like a little bit figuring out the voodoo that I'm doing. What am I doing when I multiply by the logarithm? Am I a natural log? Isn't that like a derivative? Let's think about this. What's x times e to the x mean? Right, derivative. So what does that mean? That's not that. I don't really want this. I'm just gonna do it in a different loop, like whenever I have the values on the stack. It's Z on. What are we gonna do? W. Where did I get W again? I just hate how they didn't have. How is a Wikipedia that bad? There's like no consistency between their variable naming. It's just irritating. I mean, I don't care. Whatever. I'll go look it up. But boy, woo! R squared, right? When does he use this F function? I don't really like how he's got this function in the for loop. Where the hell is he calling it?
Zeros. That piece. Just put it away aside.
Okay, all right.
So at this point, I have sampled V1 and V2 until they are within the circle. So now,
See, because you got to understand that one of them is negative, right? So you square it and it's positive, but the probability chance that they're both like, what is it? You got to look at these things as if they're like a unit circle, like, because they're probabilities, and the probabilities have to add up to 100%, right? If I sampled the probability, if I added them up, they should be around 1, right? For 12. No, it would be around the 50% mark. You added up 12. Oh, which is 0, right? So it should be around 0 when you add up 12 random numbers that are negative 1 to 1.
X, which is the equal to F with 1, is Q, right here, is which function up here, and then okay, my X, my output. So finally, I return my output. Then up here, I simulate 10,000 realizations. This should be stand up normal. And then create a plot where I go on play with the curve of the normal PDF. So if I run this is the plot again. If I just try to make different bits, oops. You can see that there are overall the bits are low. So you can see that this curve fits very, very low without distributions or different oscillations.
Okay.
And
Now that I have the right algorithm on the screen. Wait, what is the function doing? U1. And what was U1? Wait, so am I actually transforming the two numbers so that they are normal? Hmm. I'm just really freaking confused. So is it saying that these are normal? These two, whenever you add up the squares and it's less than 1. I mean, they could both be like 0.5 and it could be 1, right? Or they could both be 0.49, so it doesn't mean that they're like not correlated. And F U1, and U1 with one of these times the square root of this R squared, the logarithm of R squared. It's just, I'm just trying to wrap my mind around what are we doing. So R squared, I don't necessarily like that terminology. Maybe little r. I think he said the same thing, right? See, cause like big R to me says it's like a matrix. I don't like the capital things, capital letters that he's doing. This guy's clearly a math guy and he knows what he's talking about. So like we got a logarithm, right? So what does a logarithm tell you about the information? It means e to the x. So then log e to the x equals x, right? So what are we doing? So we had a value that's like an e to the x. Okay. And the e to the x is something you see with sine, cosine a lot. So then I divided that by the R squared variable. I personally would have called it u dot u plus v dot v. Person. I mean, it's not too bad the way it is, but u times the square root. Okay. So what do we know about this? So we know that both of the numbers, when you multiply them together, are going to be less than 1. So this is where the -2 comes at, right here, because in that region the logarithm is negative, right? So look at the so this is the region that we're in. Here's 1. So we're in a region where everything's negative. Okay. And that means e to the x. That means e to the x is less than 1. And what does that mean when e to the x is less than 1? It's shrinking. Right? It's e to the like 0.5 is like smaller than 1. E to the 1 is e. Right? E to the 1 is e. At most, you would be getting e out of this particular formula, right? So -2, that's going to get rid of our logarithm negativity. The 2, what does this do? Times the logarithm. Okay. So we did r squared plus u2, right? And so 2 of them, we have 2 of them, right? So is this like the average logarithm? Is this, so it's like, what are we saying that like these values are like e to the x plus e to the x, where e to the x is equal to like sine squared plus beta cosine, or sorry, sine plus beta cosine. You know, Euler's formula, right? Is the sine first? Euler's. Cosines first. Okay. Alphabetical order. All right. So I is this one right here. So that means that we have a real and imaginary axis. Here's the real component, and then the imaginary component's up and down. This is an oscillation. It's going to be going back and forth, okay? So we took the logarithm of r squared is, okay, so what are we doing? We're doing an e to the x thing, to where we're converting from the cosine theta plus I sine theta into our e to the x, instead of having, because we don't want to do the cosine and sine. So that's the entire point, is it's a lot faster for us to calculate e to the x than it is going to be to calculate cosine and sine, because cosine and sine are going to require these really large either lookup tables, which aren't going to be anywhere near accurate, or it's going to require two. So calculating e to the x is a lot like calculating cosine or sine. But if we calculate it up to cosine and the sine, we're basically doing twice the amount of work as what we would do here. So we're saying what? Cosine. Oh, okay. Now I see what we're doing. All right. So this e, this logarithm, what is this telling us? This is telling us theta, right? Right here. Or theta. Is that, what squiggly is that? Is that like a lowercase theta or something? Phi. P5 faux phi. So this one's phi.
Phi. Phi. Phi. Phi. Pi. Pi.
I don't know. Pi.
Pi.
All right. So, with this knowledge in hand, so we know that we have the, when we do the u squared plus u1 squared plus u2 squared, what does that do? Means if one's really big, the other one's gonna be like really small. I don't want to get stuck on this too much, but I'm almost done thinking my way through here. So I'm just trying to think about exactly what this is. So we're looking for the square root, and so the square root is where we're going. We're finding the length, right? So it's like, you know, square root of a squared plus b squared, Pythagorean theorem. Square root of a squared plus b squared. So they're saying that basically that -2 times ln r squared over r squared is equivalent to a squared plus b squared. A squared plus b squared. Because what are they saying? They're like 2 points on the unit circle. And then, so when you square them, what are you doing? This is the point where I'm like, you know, I almost got it in my head. So when I square it, it's like, just like I did a squared plus b squared equals c squared, right? Oh yeah, that's the what do you call it? The law of sines right there. So what is that, like the sine squared plus cosine squared? I remember that came in somewhere, but this is what's like kind of messing with my mind a little bit because I see u dot u plus v dot v, and then you know what in this particular situation this is like a value between -1 and 1, which is going to be a value on the complex plane. Okay. This is your real component. So our real component, are they calculating like you give me a real component and then they give you like the imaginary component? Okay, I'm done. I'm done thinking about this too much. I'm just kind of confused why this guy did this. First off, why on earth did he do this? What is W? What's that other video?
A pseudo random number.
This guy knows what he's talking about. I'm just confused. Inverse transform sampling.
Our random normally distributed variables using this inverse CDF function. So now the cumulative density function of a standard normal distribution is given like this, and we're all very familiar with this. But this leads to a problem because it can be shown that the integral of e to the power negative x squared has no closed form. So using the standard elementary functions, and that means we have no way of finding a closed form for the normal CDF. Important to note that this is a difficult distribution to work with because there are closed form inverse CDFs for the exponential, the Pareto, the Cauchy, the logistic, the Rayleigh distributions, you name it. But unfortunately, for the normal distribution, we can't. Now, thankfully, we have a workaround, and although we're unable to find that closed form solution for the inverse CDF, it's not too hard to approximate it using numerical analysis. And I've left a link here that can direct you to the right places for that. So now, thankfully, what we can do is we can demonstrate this by using the point percentile function that's actually applied in PyStats module. So we can use the point distributing pairs Z1 and Z2, and they can be obtained with the following information. So I put that up here in our Box-Muller function here, and then we've added these together. It's important to know here with the Box-Muller method that we're actually going to generate two random normal distributed variables at once. So what I've done is I've taken that in and I've divided it by 2. We can see here that we've had an incredible decrease in computation time from 3 seconds down to 0.05 now.
So what is he doing? He's adding both of them? Okay. All right.
More efficient method of actually calculating random normal variable, random numbers. And to avoid using the trigonometric function for the Box-Muller transformation, let's consider polar coordinates. So for this, we're going to consider random variables in finance 2.
Oh, but that one used the
random normal variables. So let's take a look at our distribution.
The Box-Muller. Oh, so that's what I did. I mixed up. I accidentally copied the wrong. Oh, so that's the Box-Muller one has the cosine and sine, and then the polar rejection is like the optimization of that. Is that what's going on? And the -2 comes from that, with that probability density function, because it's a negative x squared.
x2 squared plus x2 squared is less than 1. So everything falls within the boundaries of the unit circle coordinates. So picture the unit circle, and we have at the center of it, at coordinate 0, 0. What we're doing here is essentially we're getting from Pythagoras theorem, we're getting that length, that c value, and then that's w, essentially it's c squared. So the length squared of the unit circle. And what we're saying is we want to be a unit circle. So while w is greater than or equal to 1, I want to keep on sampling standard uniform random numbers until this satisfies this constraint. When it's less than 1, when it's within the unit circle, then I want to calculate my c parameter, which is the square root minus 2 log w over w, and then we can calculate our random normally distributed pairs. So I've coded that up.
And then did this one come back from that? Where'd that -2 come from? It comes from this. I don't think he goes over that, but 2ln. I mean, clearly this is like a derivative. You know, you're taking the derivative here and then multiplying it. It was a negative derivative, but since this thing is in the range where the natural logarithm is -1, then this turns into what? A squared plus b squared? I don't know. I couldn't tell you.
It's a standard close to 0, and then we've got this form 2, and you've got to get to the unit circle here. So c value, then we've got this while loop. So while any, and I'm using numpy arrays here, so we've got the sum squared function, which is able to calculate the polar rejection function here, and we've got this while loop. So while any, and I'm using numpy.
Okay, so this was the one that what's the box more? I'm gonna copy this. So what do I use? While sum squared. This is n times through the loop. Not what I want. What do I need? W. I mean, this code looks like shit if you ask me, dude. I mean, it's fucking ugly, dude. I mean, it's like two fat, ugly people with a lot of health problems had a baby, dude. And they're like close genetically relative. I mean, for real. Woo! I guess if I don't have anything nice to say, I'm not saying anything at all, right? What do I gotta do? Same sum square. It's just so just inefficient. It just makes me want to cringe just looking at this. So W is my sum square. And, this is what I need to do. I don't want to use different values than what he's using. Sum square. Okay, so what is this like? And equals. I don't like how everybody's using different things. So no, I don't do it for a multiply. I only do it for a divide. Oh, what's going on? What did I do? That'll do it, right? Oh. Got it. Natural logarithm. Didn't I just grab this? What is 10? What equals that? What is this? This doesn't look like anything markup there. Okay, here. What is this? No, yes, wait, wait, hold on. What is this doing? What does math.abs do? Is there division involved in that? Check to see whether or not we get a malicious site first before we check this tutorial out. They're securized. Taking a while. Russ took down their internet. Okay. I don't think that this one is legit. It just got spammed. I'll tell you in the documentation what I would do. I don't think that the ABS is going to take. I think it's just going to do some basic bit checking. Tolerance, what is this? What is this saying? Initial guess strategy? Dividing plus 2. I don't really want to do that with this. So this is bit shifting. I'm not going to touch this with the things. Let's hope it works. Alright, so we don't want to use that there. We use that here. Chimera case for life, baby. Y minus 1. You just call it delta. Value, isn't this parameter? Just gonna throw it over the fence and make somebody else doing, huh? That's not right. Turned out another. Okay, we got the natural logarithm, right? Between 0 and 1, the natural logarithm is negative, and it goes down to a negative infinity asymptote. EXP. I'm just confused. What am I looking at? This is where is the LM? It was E to the E. I'm just so confused. EXP using the Taylor series expansion. So when do I need to use this? So the natural logarithm. When am I using the natural logarithm? Is that for this one? I don't even have a function for it. So what are we doing with this? What am I doing? I'm training the neural network over time. So we're not doing a full e to the x calculation. We're doing part of it. But now I need to do it the fast way, huh? I could call this slow. And then we'll take another one that's faster, e to the x, and then running XOR. And I mean, I could just take my code and just rerun it. Aren't I supposed to go within the tolerance instead? So what do I do? Check it like F. Where's the calculation? Right. I don't even think I want to do this. Right? Don't I want to do... Might just have to get rid of this divide function entirely. How many times do I call it? 5 times. This I do not have. So what do I do with this? Sigmoid running error. Well, I need to hit, okay, so what's happening here? We have we did a bunch of e to the sigmoid function is you take like e to the x divided by sigma e to the whatever the hell they got on the bio, and then it turns into like a probability density, like all the neural net activations add up to 1. So I think what I do is I want to start training the neural network. I'm like a little bit lost in this other thing. What the hell does this thing do? This thing doesn't really do anything. What the hell is this? Oh, right, I'm reloading it. So I did a square root and then the running XOR changed. So I could pass it back through the stack, but it's going to be just faster to do this. Because I already have the stuff in memory. This isn't the box molar though. I think I grabbed this from Wikipedia. I don't remember what this guy's benchmark.
Right here, so we've got the sum square function, which is able to calculate W, and then we will give the condition where this, but remember, even distribute public. Whereas the pseudo-random numbers take a long time or a large number of simulated variables to actually achieve the same convergence on that price. So take a look at this graph in your own time and do your own analysis, but essentially we get large benefits from using all the random numbers in our multiplier simulation, especially when the goal is to reduce computation time and increase efficiency. Thank you very much for watching the video. If you
What does this tell us? Number of simulations and then relative error. So like whenever it goes up in error, like this is bad. So which one goes? That's the best. Quasi-oval. Well, yeah, I mean the quasi one is going to be the best. Number of simulations. That one really did. But this doesn't take into account the CPU power per. So here's the pseudo 12 pseudo box molar. So the green one, isn't that the one we're looking at? Which one's the fastest? I think the polar rejection one. See, we're looking for stuff like this for the neural network. We don't. So this black one is, you know, clearly would be the best. So that's how accurate the random number is. So, but this is going to take like way more time in order to do what we want it to do. What's the purple one? That's a quasi. So the polar rejection definitely is better. You could see the green spikes are there. It's always closer to the mean. I mean, that makes sense.
Right.
Because what is the rejection test? It's just basically the u dot u plus v dot v. And then what are they doing? Are they like? I just feel so confused by it. I might just have to take a break because for some reason I got mixed up with the two code, and I just started like using whatever my own knowledge.
And
And then,
standard uniform random numbers until this satisfies distance range. When it's less than 1, when it's within the unit circle, then I want to calculate my C parameter, which is the square root minus 2 log w over w, and then we can calculate our random normally distributed pairs. So,
random normally distributed pairs. So am I just like, am I trying to do this
coded that up in now.
and then I'm like, he's taking in a loop, going through and generating two random numbers. And then what is sum squared? And okay. All right, well, I'm going to take a break because I'm just tired, but I might come back on later. But I feel a little bit overwhelmed by the math. That whole rejection test thing is just, you know, conceptually that's difficult. Like, what are you doing? It's not really that hard. Square root, what do you mean? What are you doing when you get in the square root? You're getting the length on something like a unit circle. So it's like they're going from sine, cosine, using the e to the x trick, taking the logarithm, which is what? It's a derivative, right? Negative 2 times log w over w. Sum squared. And why would you take? So the sum squared is going to be first off, what's the antiderivative of negative 2x? Right? Negative x squared, right? So it's like ln of 2 times. Oh, is it because it's because the exponents are adding. I think I got it figured out. So we did u dot u plus v dot v, right? So we've essentially kind of like eliminated our negative dimension. That's what we're doing. So that's the bigger one. And then that one's going to go on the bottom, so we're making a ratio. And this one on the top is the derivative of what was a negative x squared, so it would have been 1 over e to the x derivative of that, which is going to be negative I'm sorry, 1 over e to the x times e to the x. So what that's doing is we took the u dot u plus v dot v, and then when we do the plug that into our 1 over e to the something plus e to the something else, what we've done is we've like averaged out the exponent values there. It's actually kind of interesting. I don't think that that guy who did the video like saw that. I saw that and I was like, this is breaking my brain. What the hell is going on? His definition, his proof was like very complicated. But what are we trying to do? Like, what's the relation of e to the x to sine? It goes, oh yeah, it's that sine square. The Euler, did they use Euler's identity, or did I just like see that this is Euler's identity and then he didn't notice it was Euler's identity? And then he had a more complicated, rigorous proof. All right, well, I'm going to take a break because I'm hungry. My stomach hurts. My bunny is being bad. I'm probably